Okay, so this is the continuation of the previous lecture. So in this lecture, let us discuss discrete time Fourier transform. So in short, we call DTFT. Okay, so we introduced the DTFT in the last class. Okay, we defined simply x of e to the j omega as the summation of x of n multiplied by e to the minus j omega n, where n is going from minus infinity to plus infinity. Okay, so this equation can be described in polar form, I mean in terms of magnitude and angle. So I can write in terms of magnitude and phase angle e to the x of e to the j omega, or in terms of the real part and the imaginary part. Let me denote the real part as x suffix r of e to the j omega, and the imaginary part x suffix I of e to the j omega. I also emphasized the fact that the imaginary part is also the real quantity, okay, even though it is imaginary part, but the imaginary part is also a real quantity. Okay, it means suppose if I write 4 plus j times 5, what about this 5? This 5 is a real number, right? Real number. It's not imaginary. The moment you put j, then j5 becomes imaginary. J times 5 is imaginary. If you consider only 5, then it is real. Okay, therefore x suffix I of e to the j omega is also imaginary. It is only by multiplication by j that you make it imaginary. The moment you multiply by j, then it makes imaginary. And we also stated that both magnitude and the real part, both are even functions of omega, and the phase angle and the imaginary part both are odd functions of omega. The other point that we made that x of e to the j omega is a periodic function, right? Periodic function with a period 2 pi, and that is the reason why we concentrate on minus pi to plus pi, our principal range, principal domain. Because of the evenness and the oddness of its parts, we concentrate only from minus pi, from 0 to pi. Once you know the behavior in this range 0 to pi, that is enough. Okay, if you know that portion 0 to pi, then we know the total spectrum. Okay, and then we considered two examples. The first example was del of n. If you take DTFT of this, then you will get 1. And the next example that we took was 1 by 2 whole to the n u of n. If we take DTFT, then this is going to be 1 divided by 1 minus 1 by 2 e to the minus j omega. Okay, in general, if you replace this 1 by 2 by alpha or some constant, alpha to the n u of n, if you take DTFT, then you will get 1 divided by 1 minus alpha times e to the minus j omega, provided that mod of alpha must be less than 1. Okay, therefore this raises the question of existence of the DTFT. Question of existence of DTFT, because for all sequences you cannot find the DTFT. Okay, the DTFT Fourier transform summation must converge in order that the DTFT exists. Okay, so this summation must converge. If it does not converge, then you cannot find the DTFT. Okay, we will come back to this a little later, but we concluded the previous lecture by finding out discrete time Fourier transform. So concluded the previous lecture by finding out the discrete time inverse Fourier transform. Inverse discrete time Fourier transform. So what is the formula for this? X of n is equal to 1 over 2 pi integral of x of e to the j omega multiplied by e to the j omega n and d omega, and the range of integration is minus pi to plus pi. And we also emphasized the fact that both DTFT and inverse discrete time Fourier transform are not matters of definition. Let me call this as equation 2. X of a to the j omega is equal to summation of equation 1 so equation 1 and 2 are not matters of definition. One follows from the other. Equation 1 follows from 2 or equation 2 follows from 1. That is, given equation 2 or given equation 1, we can find out what is x of n, or given equation 1 we can find out what is x of e to the j omega. Okay, so given x of e to the j omega we can find out x of n, given x of n we can find out x of e to the j omega. So one follows from the other. So let's talk about the question of convergence. So this is very important. For all given sequence we can't find the discrete time Fourier transform. So let us go a little bit slowly so that you will get a very clear idea about convergence. Formally, if you take this summation, obviously this sum being finite. Okay, let me write down here summation of x of n e to the minus j omega n goes from minus infinity to plus infinity. This summation must lead to a finite value, then only the discrete time Fourier transform exists. Right? Now instead of writing like this, let me write down in the following way, where n is equal to minus k2 plus k x of n e to the minus j omega n. And if this gives a finite value, then this summation will always converge. Okay, so this sum will always converge. So what we do is we allow k to go to infinity. Therefore you get back this equation 1. Let me call this as equation 1 and equation 2. The moment you take the limit as k goes to infinity, then you can go back to equation 1. Therefore limit k goes to infinity, summation of x of n e to the minus j omega n, where n is equal to minus k2 plus k. So one of the criterion is that the error if you define this quantity, okay, because this summation does not include an infinite number of samples. Okay, if you define this quantity as x suffix k of e to the j omega, and see this is x of n. If you take the limit x of e to the j omega, okay, if the summation limit is from minus infinity to plus infinity, then we wrote x of e to the j omega. Now in this, the limit is from minus k to plus k, that is why I put this suffix k. So this is limit k goes to infinity x suffix k of e to the j omega. Okay, what is the actual value? The actual value is x of e to the j omega. Okay, now I did not include the samples right from minus infinity to plus infinity. So I have considered the samples from minus k to plus k. So if you take the difference between the actual DTFT and this limited DTFT, then you will get the error. Okay, so that error is x of, this is my actual discrete time Fourier transform minus the Fourier transform of limited number of samples, finite number of samples. If you take magnitude, and this is the error. Okay, now when you take k, now you take the limit term. Limit k goes to infinity x of e to the j omega minus x suffix k of e to the j omega. Then what do you think this is going to be? The moment you allow k to go to infinity, then this k to go to infinity. If this k to go to infinity, then go back to the definition. So in this expression, if k goes to infinity, then this summation will be n is equal to minus infinity to plus infinity. Right, x of n e to the minus j omega n. Therefore, when k goes to infinity, then this guy is going to be what? X of e to the j omega. So x of e to the j omega minus x of e to the j omega becomes 0. So therefore, when you allow limit k to go to infinity, then this expression will go to 0. Okay. Right, that's it. So the error must tend to 0. So when k goes to infinity, the error tends to, so when k goes to infinity, that means you are including all the samples from minus infinity to plus infinity, and once again this thing will becomes x of e to the j omega. Already have x of e to the j omega. This minus this, it goes to 0. So let me call this is equation number 3. So equation 3 for convergence is one of the criterion, and we will show that this equation 3 is sufficient but not necessary. 3 is sufficient but not necessary. We will show this. Okay, you will see one of the sequences which always will have DTFT, which satisfies equation number 3. Okay, which satisfies this criterion, and that is x of n is absolutely summable. Whenever the sequence is absolutely summable, then that will satisfy the equation number 3. When I say absolutely summable, what does it mean? You take x of n, if it is complex, take magnitude and sum them up, right, from minus infinity to plus infinity. Then if this is less than infinity, then this is the condition for absolute summability. I mean, after adding all the infinite number of samples, you will get a finite value. That's what we mean by absolute summability. If this summation is less than infinity, then x of e to the j omega is less than infinity. Okay, this we can easily prove it. How do you prove that? By definition, x of e to the j omega is equal to summation of x of n e to the minus j omega n is going from minus infinity to plus infinity. Now you take magnitude on both sides. Magnitude, and this will be less than or equal to summation of x of n e to the minus j omega n magnitude. Suppose if we take magnitude, then this becomes the upper limit. The negative numbers also will be considered as positive number, and that will be added. That is why I put this less than or equal to symbol. So this is equal to summation of mod of x of n mod of e to the minus j omega n. By the way, this is equal to 1, where the limit is from minus infinity to plus infinity. Now n is equal to minus infinity to plus infinity mod of x of n. What about this one? That is 1, anyway we can leave it. Now we already assumed that x of n is absolute summability. Absolute summability means less than infinity. Therefore this guy is less than infinity. Okay, so therefore the right hand side I have less than infinity, the left hand side I have this mod of x of e to the j omega. Right, so now this DTFT has a finite value. That means what? Whenever the sequence x of n is absolutely summable, then the DTFT exists. Okay, if the right hand side is less than infinity, then obviously mod of x of e to the j omega will exist. Okay, if x of n is absolutely summable, then its DTFT exists. If x of n is absolutely summable, then its DTFT exists. Okay, but this condition is only sufficient. Okay, this condition is only a sufficient condition. But it is not a necessary condition. Okay, therefore x of e to the j omega magnitude is less than or equal to summation of x of n, and this is less than infinity, where n goes from minus infinity to plus infinity. Let me call this as equation number 4. So now there are sequences which are not absolutely summable, but their DTFT exists. Okay, one counter example is good enough. Okay, so there are sequences which are sequences which are not absolutely summable, okay, but its DTFT exists. That is a problem. DTFT exists. So how do you tackle that? So the counter example is provided by a sequence. For example, if you take a x of n is equal to 1 over n u of n minus 1. Okay, I cannot start from n is equal to 0, right? Because 1 by 0 becomes infinity. Because you start with an infinite sample. Now it can be shown that summation of x of okay, this one does not converge. It can be shown like this. That means summation of n is equal to 1 to infinity 1 over n does not converge. you can show this, okay? You will not get a finite value. But if you take the square of that value, let's say 1 over n squared, then this can be shown that it converges. Square summability. So n is equal to 1 to infinity. So what do you think this value is going to be? Summation of 1 over n square is equal to pi square over 6. It's a finite value, right? So n is equal to 1 to infinity. So let me call this is equation number 5 and this one equation number 6. Okay, now obviously the sequence 1 over n is not absolutely summable. Okay, therefore 1 over n u of n minus 1 is not absolutely summable, but it has DTFT, that is a beauty. But 1 over n square converges. So this is a counter example showing that x of n absolute summability is not a necessary condition, it is only a sufficient condition. Okay, the important point is absolute summability is not a necessary condition, it is only, the absolute summability, it is only a sufficient condition. Now this is an example of sequence whose energy is finite. Suppose if you take 1 over n square, what does it mean? It is energy, right? Energy of the sequence. That means you take, if you put like this x of n, then this is the energy. So energy is finite. Energy is finite means square summable. Okay, so we get the next statement. If x of n is absolutely summable, then its energy obviously less than, okay, let me write down this. If x of n is absolutely summable, what is its energy? X of n, this one, is definitely less than summation of x of n squared. Because a plus b the whole square is, a square, this one is what? This one is x of 0 squared plus x of 1 squared plus x of 2 squared plus and so on. And what about the right hand side? Right hand side is x of 0 plus x of 1 plus x of 2 the whole modulus square. And this will be always higher than this guy. Why? Because a square plus b square is always less than a plus b the whole square. Yes or no? A plus b the whole square is a square plus b square plus 2ab. So likewise this inequality I got it. So an absolute summable sequence has a finite energy. If this is less than, if summation of x of n, mod of x of n is less than infinity, that means absolute summability, then it is less than infinity. So an absolutely summable sequence is also square summable. So if a sequence is absolutely summable, then its square summable is also finite. Square summable, that is it's fine. Square summable means what? Energy. So this energy is finite. So let me write down. These are like slightly confusing terms. That is why I am spending a little more time on this. Absolutely summable sequence. Sequence I can write as summation of x of n, then absolutely square summable sequence is equal to summation of like this. But the converse is not true. Okay, in case if the sequence is no square summable, it doesn't mean that it is absolutely summable. This is true, but converse is not true. That means what? Absolute summability leads to square summable. Summable implies square summable, but square summable does not imply absolute summable. Okay, it is not necessarily absolutely summable. That's what we have shown in the example. See, 1 over n times u of n does not converge, but 1 over n square converges. That means square summability exists, but absolutely summable does not exist. Okay, so the example that we took is x of n is equal to 1 by n u of n minus 1, n minus 1. So here x of n has finite energy, which is pi square over 6, but x of n is not absolutely summable. This value is we got from square summable. However, such sequences which are square summable do have DTFT. Even though the sequences are satisfying the square summability, those sequences have discrete time Fourier transform. Okay, so and in this case what you have to find out is the following. You take x suffix k of e to the j omega minus x of e to the j omega, you take magnitude of this and this one. This is error squared, and you square it. Then you take the limit k goes to infinity x suffix k of e to the j omega. Previously I wrote x of e to the j omega minus x suffix k of e to the j omega. It doesn't matter, anyway you are taking magnitude, right? So whether you write first xk of e to the j omega or second, it's not an issue because it is a modulus operation. Now for square summable sequences, let me call, I don't know what is the equation number, previous number 5, so 6, right? The last one is 6. Let me call 7 now. This is equation number 7. Now from this equation 7, one has to go to 0. This error has to go to 0. Why the error has to go to 0? Because it is square summable. Okay, if you assume square summable, then this minus this must be equal to 0. So since we have taken magnitude square, this negative sign doesn't matter, it is a difference. Okay, you can write like this, or you can write x of e to the j omega minus x suffix k of e to the j omega, doesn't matter, both are same. Now if this equation holds for all frequencies, even then the DTFT may not exist. Okay, so we have to integrate from minus pi to plus pi. Okay, minus pi to plus pi is our range of vision. Therefore integral of limit k goes to 0 infinity xk e to the j omega minus x of e to the j omega square and then d omega, and the limit is minus pi to plus pi. And within this range minus pi to plus pi, this error in energy must go to 0. Okay, so this guy must go to 0. So this is another way of satisfying the existence of discrete time Fourier transform. That is, first we said absolutely summable sequences have DTFT, but it is only a sufficient condition. Then we said square summable sequences also have a DTFT, and the error criterion is this one. Okay, that is the error squared as k goes to infinity. In the energy, that is in the frequency domain, tends to 0 as k goes to infinity. Okay, now there are sequences. You see, if you don't take this square, then the limit may not converge. Okay, but squared the energy or error in the frequency domain converges to 0 as k goes to infinity. Okay, so now there are sequences which are neither absolutely summable nor square summable, but still the DTFT does exist. This is an important point. There are sequences which are neither absolutely summable nor square summable, but still the discrete time Fourier transform does exist. Very important point. Now let us take one example for this statement. Let's say x of n is equal to u of n. Now the question is it absolutely summable? So absolute summability means x of n, take from n is equal to minus infinity to plus infinity less than infinity. Now substitute here u of n, and here it starts from n is equal to 0, so therefore the lower limit is 0 and the upper limit is infinity. Now how many samples are there? Infinite number of samples, and each sample has the magnitude of 1. So therefore you are adding infinite number of ones. So how many terms? Infinite number of terms. Infinite number of terms. So even though you add like this, even though you add infinite number of terms, it still has DTFT. So this is equal to infinity. Okay, therefore even you can take square sum also, square summability. Therefore since it is equal to infinity, x of n is not absolutely summable, right? Now let us find out the square summability. What is square summability? X of n mod square must be less than infinity, where n goes to minus infinity to plus infinity. Summation of u square of n is equal to 0 to infinity, and this again 1 square plus 1 square plus 1 square plus up to how many terms? Infinite number of terms. Once again this is equal to infinity. The result is x of n is not square summable. Therefore u of x of n is equal to u of n, which is neither absolutely summable and nor square summable. But the beauty is it has DTFT. Okay, so in other words, square summability is also a sufficient condition. So this implies square summability is also a sufficient condition in order to exist the DTFT. So absolute summability is also a sufficient condition, and square summability is also a sufficient condition. So there are sequences which are neither absolutely summable nor square summable. For them also the DTFT exists. So this guy x of n is equal to u of n has DTFT. You can find out. And for existence of DTFT, we have to appeal to the analog delta function. So in this case, we need to appeal to the analog delta function. Okay, analog delta function not in the time domain but in the frequency domain. See, we have two delta functions, right? In the time domain, continuous time domain, we have del of t. In the discrete time domain, we have del of n. Yes or no? This is continuous time domain. This is discrete time domain. Similarly, we have analog delta function in the frequency domain. That is called del of omega, where this omega is continuous. Okay, not in the time domain but in the frequency domain. So this del of omega is a frequency domain function. Frequency domain continuous. Okay, don't confuse. So whenever you have a sequence which is neither absolutely summable nor square summable, then you have to take the help of this delta function. Okay, so the DTFT of such sequences which are neither absolutely summable nor square summable will have a delta function, that is the analog delta function in the frequency domain. And as you know, the analog delta function is defined by integral of del of omega times d omega is equal to 1, and the range is 0 minus to 0 plus. So del of omega is nothing but the limit of a pulse whose duration is delta. So this point is minus delta by 2 and this point is delta by 2, and this duration is delta, and this height is 1 over delta. Okay, so that the area under the pulse is unity, width is delta and the height is 1 over delta, so this will be always equal to 1. So del of omega is equal to limit delta goes to 0. Okay, so this is the definition of delta function. You can take this also as the definition. So this is the definition of an analog pulse function. Analog, I mean not in the time, it is in the frequency domain. Okay, it is in the frequency domain. Okay, so frequency is a continuum. So other examples of functions which do not have DTFT, if absolute summability and square summability criterion are applied, is alpha time n. Suppose if we have x of n is equal to alpha time n, for this guy also you don't have no DTFT, discrete time Fourier transform. Look at here, I did not multiply this alpha to the n by u of n or u of minus n. Alpha can be any quantity. Similarly, you can take e to the j n omega naught. Again, this is multiplied by u of n. Again, this is not multiplied by u of n. Simply I am taking x of n is equal to e to the j n omega naught t. And this e to the j n omega naught t is also neither square summable nor absolutely summable. If e to the j n omega naught t has a DTFT, obviously its real part is cos n omega naught t and imaginary part is sin n omega naught t, and then this cos n omega naught t has DTFT and the sin n omega naught t has also DTFT. So what I am saying is that for such a functions like u of n, then alpha to the n, comma, these are commas, okay, comma, e to the j n omega naught, comma, cos n omega naught, sin n omega naught. These are the examples where these are the examples which are neither absolutely summable nor square summable. Neither absolutely summable nor square summable, but this guy has DTFT exist, but the DTFT will have an analog delta functions. The DTFT contains analog delta function del of omega in their domain. So once you admit the existence of this del of omega function, then they are discrete time Fourier transformable, and for an engineer whatever works is good. Therefore, if you take the help of this analog delta function del of omega, a large range of functions are discrete time Fourier transformable. Okay, like u of n has a discrete time Fourier transform, alpha to the n, e to the j n omega naught t, cos n omega naught t, sin n omega naught t. They do exist, the discrete time Fourier transform. So we have to handle them, and therefore we admit this analog function del of omega. That is, in their discrete time Fourier transform, the del of omega function will exist. Okay, for example, if you take e to the j n omega naught discrete time Fourier transform, now you can show this is equal to 2 pi times del of omega minus omega naught plus 2 pi k, where k is equal to minus infinity to plus infinity. Okay, so the discrete time Fourier transform of e to the j n omega naught t contains a chain of delta functions. Okay, the delta function at omega is equal to omega naught, right? And omega is equal to omega naught minus 2 pi, omega naught plus 2 pi, omega naught minus 4 pi, omega naught plus 4 pi, and so on and so forth. So you take e to the j n omega naught t and find its discrete time Fourier transform. It's not easy, okay? So finding e to the j n omega naught t to this guy in the forward direction is not easy. Not easy to derive. But in the reverse direction, it is easy. If you come from frequency domain to the time domain, it is easy to show. Okay, because in the forward direction you have to invoke theory of distributions from mathematics, something called a theory of distribution. It is not easy to show and it is not needed also as an engineer. But as you know, the discrete time Fourier transform is a one-to-one transform, that is x of n and x of e to the j omega are one-to-one transform. Then if you prove that the inverse discrete time Fourier transform of x of e to the j omega is x of n, then this is good enough proof. Agreed? So because this is necessary as well as sufficient. If you go in the reverse direction, easy for certain functions. In the forward direction, difficult. Okay, so and we know that this x of n and x of e to the j omega are one-to-one transformation, and in such cases it is easier to find the inverse DTFT of the given function. Now this is given. From this, can I find out x of n? X of e to the j omega is equal to summation of 2 pi del of omega minus omega naught minus 2 pi k, where k is equal to minus infinity to plus infinity. Now how can you find out x of n? Simply take the definition. X of n is equal to 1 over 2 pi integral minus pi to plus pi x of e to the j omega, that is summation of 2 pi del of omega minus omega naught minus 2 pi k. Is it minus 2 pi k or plus 2 pi k? I am sorry, this is plus 2 pi k. Plus 2 pi k e to the j n omega naught, sorry, n omega d omega. Okay, now you can simplify this. So how will you simplify? In this summation, you have to consider only one term, right? Here k is an integer, right? K is equal to minus infinity to plus infinity. So k is an integer. So my range of vision is minus pi to plus pi in the integration. Okay, the integration is minus pi to plus pi. In this minus pi to plus pi, there is only one integer, which is k is equal to 0. Okay, k will be equal to 0. This is the base band. When k becomes 1 or minus 1, then it will goes out of range of vision. The integration will be 0. Okay, I need to consider only k is equal to 0 in this integration. In case if you take k is equal to 1, then what is going to happen? You substitute here. Okay, k is equal to 1, then it becomes del of omega minus omega naught plus 2 pi. So in the frequency axis, this is 0 and this is pi, and this will be omega minus omega naught plus 2 pi. So it lies minus 2 pi. This is minus 2 pi, and let's say this is minus pi, and this is omega naught, omega minus omega naught plus 2 pi. So this is my range of vision. Here k is equal to 0, and this point is k is equal to 1, k is equal to minus 1, and this point is k is equal to 1. So when you take k is equal to 1, my delta function lies either above the plus pi or below the minus pi. It falls outside of my range of vision or range of integration. So therefore only one value exists in this integral, that is k is equal to 0. Therefore this is going to be 1 by 2 pi minus pi to plus pi. In this summation I have infinite number of terms. Out of infinite terms, I have only one non-zero terms, that is 2 pi times del of omega minus omega naught, because k is equal to 0 there, e to the j n omega naught d omega. Now it's this 2 pi and this 2 pi will get cancelled. So this is integral of del of omega minus omega naught e to the j n omega naught d omega. This is a standard integral, right? So whenever you have a function like this, then this is going to be when you have del of omega minus omega naught multiplied by f of omega into d omega, this is equal to f of omega naught. This is a standard result. Similarly, del of t minus t naught f of t times dt is equal to f of t naught. This is a result which you recall from your signals and systems course. This we proved also. So this is equal to, I'm sorry, this is not omega naught actually, by the way, this is omega. Yeah, same mistake I am repeating. Omega. Therefore, this omega is replaced by omega naught. So you will get e to the j n omega naught. So x of n is equal to this value. So we have proved that the inverse DTFT of this summation, where is it? This summation is e to the j n omega naught. In many cases, this is the story. Okay. So in fact, you can prove yourself, as if you take the sequence 1, then this is my x of n. Its DTFT would be del of n. U of n becomes 1 divided by 1 minus e to the minus j omega plus summation of pi times del of omega plus 2 pi k. K is from minus infinity to plus infinity. Okay, if you move in the forward direction, for this case it is very difficult to find the DTFT of u of n. Okay, OpenM has a proof, so I suggest you to look at it. Okay, as I said, u of n is neither absolutely summable nor square summable, and therefore we have to bring the delta function. That is why this delta function is coming here. So one of the ways to understand this DTFT is that this portion takes care of the summation. Okay, so this portion is nothing but 1 plus e to the minus j omega plus e to the minus j2 omega plus e to the minus j3 omega, and so on and so forth. But this summation does not take care of the average value of u of n, because what is your discrete DTFT? Summation of x of n e to the minus j omega n, summation of u of n e to the minus j omega n. So this is summation of u of n is 1, right, from n is equal to 0 to infinity. So e to the minus j omega n is equal to 0 to infinity. So if you expand this, you will get 1 plus e to the minus j omega n plus e to the minus j2 omega n plus e to the minus j3 omega n, and so on and so forth. So this goes up to infinity. Therefore this will be equal to 1 divided by 1 minus e to the minus j omega. Fine. What about the average value? Average value of u of n. The average value of u of n is 1 by 2, right? Average value of u of n is equal to 1 by 2. Therefore, if you take 1 by 2 as DTFT, what do you get? 1 by 2 times summation of 2 pi del of omega minus omega naught plus 2 pi k. This is what we proved initially, right, in the previous case. Sorry, omega plus 2 pi k, I'm sorry. 1 minute. 2 pi k. This 2 and that 2 will get cancelled. You will get summation of omega plus 2 pi k. This is what exactly you got here. This one is here. And this infinite sequence we got from here is there here. Therefore, the Fourier discrete time Fourier transform of u of n contains two parts, 1 divided by 1 minus e to the j omega, and then you have summation of pi of del of omega plus 2 pi k. Okay. In a similar manner, we can continue this table. E to the j n omega naught has discrete time Fourier transform 2 pi del of omega minus omega naught plus 2 pi k. K is equal to minus infinity to plus infinity. Then alpha times alpha to the n u of n has the Fourier transform 1 divided by 1 minus alpha e to the minus j omega mod of alpha less than 1. Then u of n, this just now we wrote this, right? 1 by 1 minus e to the minus j omega plus summation of pi times del of omega plus 2 pi k, where k is minus infinity to plus infinity. Then del of n is 1. Okay, therefore this table gives you the basic sequences and their discrete time Fourier transforms. In other sequences can be expressed in terms of these sequences, basic sequences, like cosine sine can be sine or cosine or any exponentials can be expressed in terms of these guys. Okay, if you have delta functions, then can also be taken care of. Okay, so let's take an example. I suggest strongly that you verify this table, okay, for yourself. Questions like what will be the DTFT of u of minus n, or what is the DTFT of alpha n times u of minus n, right, and things like that. So once you admit existence of a DTFT, and all properties will be valid. Okay. Okay, I take an example. My favorite example is upsampler. Okay, y of n is equal to x of n by L, where n is equal to 0 plus or minus L plus or minus 2L and so on and so forth, and 0 otherwise. This is my upsampler. Now the DTFT is given by y of e to the j omega is equal to summation of x of n by L e to the minus j n omega, where n is equal to here n will be restricted to not 0, 1, 2, 3. It can be 0 plus or minus L plus or minus 2L plus or minus 3L and so on and so forth, because I don't have value in between 0 and L because of the upsampling property. Of course it goes to infinity, but only discrete values of n. This n goes up to infinity, but it takes only the limited number of values. The sequence x of n by L is non-zero only when n is equal to 0 plus or minus L plus or minus 2L and so on and so forth. So what are the in between samples? There are L minus 1 0 samples. They will contribute 0 in this summation. They will contribute 0 in this summation. So and to see what is the summation leads to, let's put n by L is equal to m, some other quantity which is an integer. Okay, so Therefore, your summation now becomes x of m e to the minus j m suffix l omega. And now the limit is m is equal to minus infinity to plus infinity. And look at the definition. Where is the definition? Okay, let me write down the definition so that we can compare it. Summation of x of n e to the minus j omega n. Right? Now if you have omega here, then you wrote the entire thing as x of e to the j omega. Yes or no? If you have omega here, then it becomes x of e to the j omega. Now instead of omega, I have L also here. So in addition to omega, I have L here. Anyway, this m is a number, okay, it's a variable, right? Here also m and here also m. Here also n and here also n, it doesn't matter. See, here is n, m and here also m. It's a dummy variable. And this is n and this also n. It is also dummy variable. So we are not looking at the dummy variable, we are looking at the omega. If you have omega here, then this is x of e to the j omega. Now instead of omega here, I have L omega. So therefore this whole thing I can write as x of e to the, instead of omega I will write L omega. Okay, that's what I want to write down here. So on the left hand side, y of e to the j omega, then this is y of e to the j omega, that's all. And therefore we have shown for an upsampler the spectrum y of e to the j omega is related to the original sequence x of e to the j omega by this relationship. Okay, so let's draw a few pictures and we can understand in a better way. A picture is worth 1000 words. I said the discrete time Fourier transform is a periodic function. Let me take my function is like this. It is periodically repeating like that, and like this. This is x of e to the j omega. Right? It repeats after every 2 pi. So this is 0. Let's say the upper frequency is omega h and the lower frequency is minus omega h. And this point is, let's say, pi, and this one is minus pi. And this is 2 pi, like that. Minus 2 pi. If I take the spectrum of y of e to the j omega, how does it change? It changes like this. This is omega h by L and this one is minus omega h by L. And you will have one more spectrum. This is this point is 2 pi by L and this point is 2 pi by L plus omega h by L, and this point is, you can calculate, okay, it's very easy to calculate, and this point is 2 pi minus omega h by L. You see, it would be the same shape does not change, except that the end points will be omega h by L and minus omega h by L. The next one will occur at 2 pi by L. So this point is going to be 2 pi by L plus omega h by L, and this point is going to be 2 pi by L minus omega h by L, and so on so forth. So the spectrum is compressed here. Spectrum is compressed. So what existed between minus omega h and plus omega h is now compressed to minus omega h by L and plus omega h by L, and therefore up to pi I mean from 0 to pi, okay, this point is 0 and this point is pi, 0 to pi. How many such repetitions will be there? Obviously L minus 1 repetitions. So what existed between minus omega h and plus omega h is now compressed to minus omega h by L and plus omega h by L. Therefore I have L minus 1 repetitions. Okay, whereas from minus pi to plus pi there was only one sample here. See, only one sample, only one repetitions. In the upsampled version you get repetitions from 0 to pi, and your basic range of vision has multiple copies of this spectrum, and this creates problem in upsampling. So in upsampling you necessarily have to follow the upsampler by a low pass filter. Okay, to remove this guy I need to get rid of this guy. Similarly in the left hand side I also have the samples like this. I need to get rid of this. So put a low pass filter such that it passes only minus omega h by L to plus omega h by L. This portion alone will be passed by the low pass filter. Therefore you choose a low pass filter with cutoff frequency omega c is equal to omega h by L, or slightly more, okay, slightly more than omega h by L, but before the next spectrum starts. So the upsampler is also a spectrum compressor, and the difficulty with the upsampler is not difficulty, the solution to this so called repetition problem, which is also aliasing. That is, higher frequency now poses lower frequency. So this distortion is also aliasing distortion. Therefore the upsampler has to be necessarily followed by a low pass filter in order to remove these guys and next guys and next guys and so on and so forth. Therefore the baseband spectrum, this is called a baseband spectrum. Therefore the baseband spectrum is retained with the help of low pass filter, and all the rest is deleted or removed by the low pass filter. Otherwise your further processing will give you unreliable results or nonsense results. Okay, so before we go further, let us take another example. This is also interesting example. Find inverse discrete time Fourier transform of x of e to the j omega, which is equal to j times sine of omega multiplied by 3 plus 4 times cos of omega plus 2 times cos square omega. Now how do you proceed this? Now obviously in general case you will have the integral, right? What is the inverse integral? X of n is equal to 1 by 2 pi integral of minus pi to plus pi x of e to the j omega e to the j omega n d omega. Now if you use this inverse discrete time Fourier transform formula, then you will be trapped. Okay, you cannot get the answer very quickly. Therefore you don't need this formula here. Okay, all that you require is you have to express what I call all you need to do is you have to express this guy, this given equation, in terms of summation of x of n times e to the minus j n omega. with the appropriate appropriate limits of n. Okay, and here n goes from minus infinity to plus infinity. Okay, so all you require is you have to find out x of n, that is the coefficient of e to the minus j n omega naught. So in this given problem, express in terms of e to the j times n omega naught, where n is an integer. N can take 0, 1, 2, 3, minus 1, minus 2, minus 3, and so on and so forth. So this is the example where the integral should not be used. This integral should not be used. There are examples where you are most welcome to use this integral, but there are places where you should not use it. So by looking at the problem, you should be able to recognize that x of e to the j omega can be very simply written, and so that you can find the x of n sequences. So therefore from this you can write as follows: x of e to the j omega is j times sin omega. I can write e to the j omega minus e to the minus j omega divided by 2j multiplied by 3 plus 4 times cos omega becomes e to the j omega plus e to the minus j omega by 2, and 2 cos square omega becomes 2 times e to the j omega plus e to the minus j omega by 2 whole squared. Now you can expand this, j and j get cancelled, e to the j omega minus e to the minus j omega divided by 2, and multiply this 3 plus 2 times e to the j omega plus 2 times e to the minus j omega plus this is going to be square root, right? E to the j2 omega plus e to the minus j2 omega plus 2 divided by 2. Okay, now you simplify this and find out the coefficient of e to the minus j n omega n omega. And if you simplify this, let me write down the final answer: 1 by 4 e to the j times 3 omega plus e to the j2 omega plus 4 by 7 e to the j omega plus 0 times e to the j times 0 omega plus 9 by 2 e to the minus j omega minus e to the minus j2 omega minus 1 by 4 e to the minus j3 omega. Now look at the coefficient of this guy. What is the coefficient? 1 by 4, and this corresponds to n is equal to minus 3. And then what is the coefficient of this? 1. What is the corresponding n value? N is equal to minus 2, and here n is equal to minus 1, and here n is equal to 0, and here n is equal to plus 1, and here n is equal to plus 2, and this n is equal to plus 3. So the coefficients you can write down. These coefficients are nothing but x of n, because what is your DTFT? X of e to the j omega is equal to summation of x of n e to the minus j n omega naught, right? So if you expand this, x of minus 3 e to the minus into minus plus j3 omega plus x of minus 2 x of j2 omega plus x of minus 1 e to the j omega plus x of 0 e to the j0 omega plus x of 1 e to the minus j omega plus x of 2 e to the minus j2 omega plus x of 3 e to the minus j3 omega. Now compare term by term. So for e to the j3 omega, my coefficient is 1 by 4. Therefore this 1 by 4 corresponds to x of minus 3. and this 1 corresponds to x of minus 2, and this 4 by 7 corresponds to x of minus 1, and this 0 corresponds to x of 0, and this 9 by 2 corresponds to x of 1, and this minus 1 here, this minus 1 corresponds to x of 2, minus 1 by 4 corresponds to x of 3. So let me write down these values. So therefore x of n is equal to 1 by 4 comma 1 comma 4 by 7 comma 0 comma 9 by 2 minus 1 minus 1 by 4, and the location of the 0 must be indicated by an arrow, so you put an arrow here. This n is equal to 0, so you must indicate where the pivot is. Okay, so this is my pivot location, pivot, pivot. Pivot. So given a problem, either to find the DTFT or inverse discrete time Fourier transform or proof, you have to decide which way to go, how to go about it. Once you understand the problem and find a clue, the first step is understand the problem and then find the clue. Okay, then the rest is algebra. Nothing to worry much. Okay, I suggest you don't make mistake even in the algebra also. Okay, so that's it about discrete time Fourier transform and inverse discrete time Fourier transform, and when it converges and when it doesn't converge. Even if the sequence is neither absolutely summable nor square summable, it has discrete time Fourier transform, but you have to include the analog delta function. When I say analog delta function, I mean the frequency in the delta function, the frequency domain, but again this omega is continuous, not discrete. So let me stop at this point. In the next lecture we will discuss the properties of DTFT. Okay, so let me stop at this point. Thank you very much.